Hi, and welcome back to Codex. Today's speaker is Hrushikesh Mhaskar from Claremont Graduate University. Professor Mhaskar is an expert in approximation theory and harmonic analysis. Today, he'll talk about local analysis of global data. Take it away, Professor Mhaskar.
Okay. Thank you very much for the invitation and the nice introduction. Oh, you have a problem. Let's see. Why is this not working?
You might need to click.
Okay. Pardon? Yeah, okay. I think I can manage with mouse. So this is the outline of my talk. I will first talk about something which was called my idiotic quest, that I want to do local approximation based on Fourier coefficients, which are essentially global. And then I will talk about some more recent applications to signal separation. And then there was an insight which was developed a few years ago that I can think of classification problems in machine learning as generalizations of signal separation problems. So that would be the last topic of my talk. Okay, so here is the motivation. Let's think of this function cosine x to the 1 quarter. It's analytic on minus pi to pi except at 2 points. If I look at the Fourier coefficients of this function, then I don't see anything bad happening to this function at any points. Or it actually reveals nothing at all about the local behavior. But if you look at the wavelet coefficients, then it is very clear that there is something bad happening at pi over 2 and minus pi over 2. So in 1990s, Charles Chui came to visit me and he was trying to teach me about wavelets. And my immediate question was, yeah, okay, but the Fourier coefficients don't give any information by themselves, but they do contain all the information about the function. So how can we, the question is not so much whether or not to look at Fourier coefficients, but how to use them to get this kind of information. Don't understand. The other problem which I was interested in is, again, look at this function. If I look at the Fourier projection, which is the best approximation in L2, then just these two bad points are affecting the errors even if I go far away from these points. So even if I increase the degree to 256 from 64, the approximation away is not increasing that much. By the way, this is a log plot. Can we do better? And this is, of course, an old project. I'm talking about some very old work. As you can see, this was the slogan by Obama. And I made that slogan before Obama did. Okay, so, oops, now what? Yeah. So the techniques which I'm going to develop here will give me this sort of rate of approximation. As we increase the degree 2 times, then you see that we are getting a substantial improvement when we go away from these bad points. We have to pay for it near the bad points. So if you are used to measuring error in L2 norm or sup norm, then it will not do as good. But if I look at the percentage of points at which the error is small, then with our method, the percentage increases from 9% to 79% as the degree goes from 63 to 255. The Fourier projection gives only a 3.52% points where the error is less than 10 to the minus 4. So that's the motivation for localized kernels. So this is a notation, and this is kind of a bad notation because I will be using f hat later on to denote some kind of an estimator of f. But in this part of my talk, f hat will be Fourier coefficients. And then I'm interested in uniform approximation, in fact, pointwise approximation. But nevertheless, this is how the degree of approximation is defined in the sup norm. And there is a very famous theorem dating back to 1912 or something like that, or maybe 45, but surely a very ancient theorem dating back to the time before I was born. So we take an arbitrary gamma and split it into its integer part and fractional part. Then the degree of approximation decays like this if and only if S continuous derivatives and they satisfy this Zygmunt-Lipschitz condition. If you notice, this requires the group structure on the circle. This definition doesn't require anything. So in approximation theory nowadays, I prefer to define the smoothness of the function using the degrees of approximation rather than thinking about derivatives and Lipschitz continuity and those kind of things. Okay, here are two functions. This is a piecewise analytic function as before, and this is a nowhere differentiable function. Both of them are in this class W half. But if I define local smoothness in this way, that I put a cookie cutter function and then require that f times that phi should be in the smoothness class, then this function belongs to W gamma of x0 for every x0 not equal to plus minus pi over 2 and every gamma which is positive. So it is really a very smooth function outside. And this function does not belong to any of these local smoothness classes. So I had a neighbor who invited me to their church and saying that there is a function in their church. So I was hoping that the function would be more like f1 and not like f2. And then it turns out that they mean something completely different by the word function after all. Anyway, so the question is, how do we distinguish between these functions if you only know their Fourier coefficients? Okay, so then the trick is to use a low pass filter, which for me is a smooth function equal to 1 on this part and outside it is 0. So if I use this like a filter, it will reproduce trigonometric polynomials of order n over 2, and it will be itself a trigonometric polynomial of degree n. So I will define a filter like this. Because of the Poisson summation formula, it's not hard to deduce that this kernel has this sharp localization property. This holds in theory for every capital S, but then the constant will depend upon S also. So globally, this looks very much like a needle. If you go away from the origin, then you see that it's practically exponentially decreasing as the degree increases. So here is some more notation. In former times, it used to be called a summability operator, and you can find such a thing already in Hardy's book on divergent series. But now I'm told that I should use reconstruction operator, because if I say summability operator, then some people might go to sleep. Okay, but the nice property about this is you remember that this h was a constant from minus n over 2 to plus n over 2. So it is reproducing polynomials of degree n over 2. And so we have a good approximation. Not the best approximation, but if you are only interested in the part where the degree of approximation is converging like n to the minus gamma, then this does the job. Okay, then the analysis operator is very simple to construct. We just take the difference of two consecutive things. And the important thing to remember is that the sigma was computed using Fourier coefficients of f. And so the tau is also computed using the Fourier coefficients. And then I need one more kernel to bring it all in consistency with wavelet analysis. So these are the usual Fourier quadrature points. I define these coefficients as the values of this tau j f at vjk. Remember that tau j is computed using Fourier coefficients, but I'm then evaluating this transform at these special quadrature points. And then we get a double expansion, just like in wavelet analysis. We don't have a single mother wavelet and dilation, but we have a separate mother wavelet for each dyadic split of the Fourier domain. But still we have a complete discrete expansion just like in wavelets. And we have this frame property. The nice thing about this expansion is, unlike Fourier coefficients, the coefficients in this expansion completely determine the smoothness of the function. So our function is in this smoothness class if and only if these decay like 2 to the minus j gamma. Okay. The surprising thing is, even if these tau jfs are defined using Fourier coefficients, even the local smoothness classes are determined completely by these coefficients. This function will belong to a local smoothness class if and only if in the vicinity of that point the coefficients behave like this. So it achieves in some sense the time frequency localization. The frequencies are increasing by 2 to the j, but the time is shrinking. And this is the diagram for the tau CJK coefficients for this function for j equal to 5, 6, and 7. So you see that it is determining the bad points very sharply, just like wavelets did. But we have increasing number of vanishing moments. So even if we have a function which has fifth derivative with jump discontinuity, our tau transform can still detect where those are. Compactly supported wavelets will reach a saturation because they can only have finitely many vanishing moments. In fact, we have a result which says that we can detect analytic singularities. So if the function is piecewise analytic, then we can figure out where it is not analytic. Also, the approximation is adjusting automatically. We don't have to first find the singularities and then split the domain and do approximation differently on different domains. The degree of approximation adjusts itself automatically.
Sorry, if I could ask a question.
Sure.
On that previous slide, will this work well if the singularities aren't symmetric about the origin, or is that being used somehow?
No, it's not used. You can do it non-symmetrically also.
Okay, thanks.
In Daubach's book, she had an example of square root of absolute sin x. So I just adopted that example for illustration. Okay, so our frames have at higher and higher level have higher and higher number of vanishing moments, so they don't have saturation. The other interesting thing is they are behaving in an opposite direction from wavelets. So when we do wavelet analysis, then we already have a large number of samples, namely all the pixels in the image. Here we are computing the coarse approximation with small number of samples, and then the tau j's are computed with increasing number of samples. So we are adding features when more and more data becomes available. And of course, the constructions can be made with random data. We don't have to have these equidistant data. Okay, so that was some old work which I had done in 2005 or something like that. Here is a little bit more modern application. So we are looking at a linear combination of Dirac delta measures on the circle. And the question is, we are given finitely many noisy Fourier coefficients. And we want to figure out what is the k and what are the lambda k's. Once we get k's and lambda k's, then we can figure out a sub k's just by using linear least squares. So the important problem is to get lambda k's, but then we also need to get capital K. So this is a very old problem dating back to 1795, and there are many methods to do this problem. Some of the latest methods are called Esprit method, but it turns out that our method is more stable under noise, and then it works more accurate answers. So the approach here is to just take the same sigma sub n operator but applied to the major mu now, and then look at the peaks of this spectrum. And because of the localization properties of our kernel, this expression will approximate mu in the weak star sense. limiting quantities here are, oops. The minimal separation among these frequencies and the minimal amplitude. So of course, if one of the amplitudes is very small, then it will be hard to detect that frequency. And likewise, if the frequencies are very close to each other, then that's basically the super resolution problem. Oh. Oh, yeah. So here is one example. We need to treat this minimal separation and threshold as tunable parameters. So we looked at this example where there are very close by frequencies, and we added a large noise of SNR minus 5 dB. And these are the graphs of the operator which I showed you. The question was where to set the threshold. When you have a small value of n, then you see that there is too much noise which is drowning out this small amplitude signal. If we increase the number of Fourier coefficients we have, then the noise is substantially reduced. And then even with a small threshold, we can detect both of them accurately. Let me show a close-up for this frequency, which is very close by. Oh, I don't know how to make this smaller now. Okay, so this is the example which I was looking at. I have no idea now how to make it smaller. Anyway, let's try. So again, here is a close-up against x equal to 2 where there are two very close by frequencies. If I just deal with 512, and then we cannot separate those frequencies. If the n goes up to 1024, then we can separate them, but then one has to look carefully. If we increase it to 16384, then we can detect both of them very clearly with a small threshold. So it's not super resolution in the strict sense. I'm definitely sampling at a far higher rate than the Nyquist rate. But the point is with the very high noise level, we can still separate these very close by frequencies. Here is another example. I don't know how to... let me stop sharing and come back again to, and then share it again. Okay. Oh well, the SNR is minus 20 dNB, so the original signal looks like this. After we apply our sigma operator, and I don't remember how high the degree was, but we can clearly distinguish between all the three frequencies, even if they are very close and the noise level is tremendous. Okay. So the next question, which is even more recent and probably still of recent interest of investigation, is what is called the blind source signal separation. The problem is like this. We have a signal which is a superposition of k signals. They are all dependent on time, and then we are adding some noise to that. And each of this, of course, is a complex valued signal, so it has an amplitude part and a phase part. Once more, the question is, okay, phi k prime is defined to be the instantaneous frequency. So the problem is we are given equidistant samples of this capital F, and we have to find what is capital K and what are the F sub k's and what are the instantaneous frequencies. If you think about it, there is an even bigger problem here, that this problem doesn't make sense. Because you have a complex valued function, it already has an amplitude and a phase automatically. So what does it mean to say that it is a sum of capital K components? Yeah, But okay, that just because the problem doesn't make sense, that doesn't stop people from talking about it. And then there are a lot of techniques developed for this. Partly, yeah. So there is a very famous technique called empirical mode decomposition, but it is a very empirical technique. There is no theory behind it. The first theory which I'm aware of was introduced by Ingrid Daubechies and her collaborators. So that's the synchro-squeezing transform. It was based on something similar to what our summability operator was doing, but it was more wavelet based. And of course, it's based on very solid theoretical background. The only problem which I could see was it was a very complicated construction. But anyway, the assumptions are that in the vicinity of any real number, the amplitudes are approximately constants, and so are the instantaneous frequencies. So if that is the case, then the problem reduces to the constant frequency, constant amplitude problem, which I talked about before, and then it makes perfect sense. So what I observed was in the SST work, this vicinity meant the entire real line. In my work with Charles Schmidt, the vicinity was just a neighborhood of T star. I have a problem here. I don't see my entire slide altogether. Oh, okay. So here are the references. This idea was introduced in the paper by Daubechies and Mice in 1996, and they developed that into SST in 2011, and Charles and I did some further work on it in 2016. Okay. So in my paper with Charles, we defined what we have called a signal separation operator, which is basically the reconstruction operator which I showed you before. So again, we consider this measure, but now it's a function of time. At each time, I have a different measure. And then because of our assumptions, our signal is going to be approximately equal to this signal. So now these are considered constants because I'm at T star, and then it's a point source signal separation problem. So we use the same idea which is used for point source signal separation. Okay, I forgot to add an absolute value here, but it doesn't matter because it is a even function. So when I plug this mu star and apply the reconstruction operator before, then this is the expression which we got. This is what we call the signal separation operator. It's approximately the same as the point source signal separation thing. And so for the same reason as before, it will converge in the weak star sense to this mu T star. Okay, so here is a theorem. Of course, a theorem will require a lot of notation. The important things are this minimal magnitude as before and minimal separation. And then there are some other notations just to simplify matters. So if we use this notation, then the mu hat L is just the same as what we have already seen. Previously, we did not consider noise, but in my new paper with my pupils Kitty Moon and Eric Mason, we have studied the probabilistic estimate on this too. So if my n is greater than some constant times the reciprocal of the minimal separation and the variance of the noise satisfies this condition, and then I choose a subinterval so that this condition is satisfied. That controls the approximation of the signal by constant amplitude, constant frequency signal. And then I consider this thresholded set. Remember, I don't know what is scriptive, but I will talk about this momentarily. So then with high probability, this set is a disjoint union of exactly as many subsets as there are components. Each of these components has a diameter not exceeding C over N, and N is proportional to the reciprocal of the minimal separation. So the distance between those two is greater than minimal separation over 2. That helps us to use ready-made functions in MATLAB, Python, and whatnot to figure out what those subsets are. And then each of these subsets will contain an interval of this length. That's another clue to how to detect these subsets. Okay, and then of course, if I consider the point at which the maximum of this SSO operator is taken, that will determine the instantaneous frequency. And as I said, this is not a notation which I like, but that's what everybody uses to the hat is denoted to the hat denotes the estimator of the lambda sub L in this context. But it also denotes Fourier coefficient sometimes. So one has to take it with the context. Okay, so together with my pupil Yak Kittumun, we decided to try it on linear chirp models. So we have a pulse of this form. The problem is this pulse is discontinuous. So the assumptions for the SSO paper or the SST paper certainly don't apply. And then our signal is given like this. Eric Mason generated a code for us to generate such a signal. And then the idea was to apply this SSO to overlapping snippets of the noisy signal. So the idea behind the SSO was that our signal is piecewise constant, which is still true here, except at the breakpoints. So we take a sufficiently small interval and look at the snippet of this signal in this interval. Then we imagine that except at the endpoints of this interval, the assumptions of SSO will be satisfied. And so we then construct our SSO operator and look at the estimator of the frequency as before. And then here is a signal where this is the ground truth for the instantaneous frequencies. You see that there is an intersection and there are discontinuities, and the signals have different lengths. And then on the top of that, we have added a minus 30 dB SNR noise. So it was considered a challenge. And then it turns out that our SSO operator does remarkably well. We just have to figure out how to choose these tunable parameters. So we developed an idea that at each point we will take this SSO operator, then we draw the histogram of the peaks, and then figure out where to threshold the noise by looking at a certain breakpoint in this histogram. So Yak decided to take 99% percentile. Okay, so that's at one point. We have to do this at each and every point at which we are looking at the snippet. Oops. Yeah. So when we do that, the peaks form a diagram called the SSO diagram. On the x-axis is the point t star at which we are applying this algorithm. On the y-axis is the frequency. And you can see that because the noise is so large at minus 30 dB, there is a lot of aliasing which is going on, but then not in the range where the actual frequencies are. And so then we can use dbScan algorithm from MATLAB to figure out where exactly this region is. And then we can refine it. So then we get this kind of clusters as predicted by the SSO theorem. And then once more use dbScan and find peaks to get these clusters. Okay. The problem then is we have some intersecting frequencies here. So the conditions of the SSO theorem will not apply. Our frequencies are not well separated. The new thing which was very surprising and pleasant for me was that we can turn this failure into success. So because we know that our theorem doesn't apply here, we can figure out where the errors are bad. And the only reason why the errors are bad could be only because the assumptions of the theorem are not satisfied. So then we can figure out where to focus on. And then we focus further on this and remember that at this point there is not much noise left over. So then we can figure out where are these lines where the thing is still well separated corresponding to this finer partition. When we find out what these lines are, we can fit the least squares to get the parameters and then do some matching to figure out how to extend this line and connect it with this line and how to extend this to connect with this. And then we get this result, which is almost like the ground truth. Okay, then how to compare it with SST? So we found one paper by Haotiang Wu and Thakur where they gave there was an online available algorithm. So I tried to use that. And this was the signal they had given for testing their result. So just to make sure that there was no mistake in applying this SST algorithm, we tried it with different noise levels. And you see that when the noise increases, then it can still detect these intersecting frequencies, but that gets more in the eyes of the beholder. When we apply it to our signal, then we don't see anything. Even with 0 dB SNR and 0.5 gigahertz sampling frequency. If we go beyond this sampling frequency, then the algorithm which we found online takes forever to run. Okay. So that was the application to signal separation. Then this is a new exciting thing which I discovered together with Alex Cloninger a few years ago, that we can treat classification also using the same ideas as super resolution. And then I had another brilliant student called Ryan O'Dowd who developed this further and did experiments especially. So the classification problem, as everybody knows, we are given samples like this coming from some unknown probability distribution, and the Weigels are restricted to certain finite set of labels. And we are supposed to find a classifier so that for a new point x, f of x is the label for x. This has been traditionally treated like a function approximation problem, but there are some difficulties. One is that the class boundaries can be rough, and they might even touch or even overlap. And so if we think of this classifier as a function, the function cannot be extended smoothly and certainly not constructively. So as you remember from the beginning of my talk, the approximation theory results all require that the target function should be smooth. That condition is not satisfied here. It cannot be satisfied sometimes. So the alternative insight which I had was, suppose there are, let's take the example of these two classes, birds and airplanes. We are observing samples from a convex combination of these two measures. So the airplanes are coming with a probability measure mu1, the birds are sampled according to probability measure mu2. And then we are getting this sample. So then the idea is, can I separate the supports mu1 and mu2? If I can separate the supports of these two measures, then without looking at the labels, then I just have to query one label from here and one label from here, and then I'm done. The idea is that when we use deep networks or neural networks for this purpose, then we need a tremendous amount of training data to train them properly. If you are training a child and you show him 1,000,000 cats and 1,000,000 dogs, then the child will just start crying. It won't understand how to separate cat or dog. Anytime he sees any animal, he will just start crying. So how does the child learn which is a cat and which is a dog? We take him for a walk, and then it shows two different objects and ask, what is this and what is that? And after a few such questions, then it starts understanding what is a cat and what is a dog. So the idea was to mimic that kind of approach. We figure out which of the what are the supports of these two classes, and then we just sample judiciously among each of the supports. Okay, so again, the idea is to use the same thing. We use our localized kernel and find the sigma sub n. In this case, we have to estimate it rather than using Fourier coefficients. But that's another problem, how to estimate this and keep track of the errors. Okay, so here I'm looking at the circle. So I imagine that my classes are disjointly supported, and because of the localization property of this kernel, if we are near the support of 1 mu k, then this object will be large, like having the peak in the point source signal separation. If we are away from the support, then all of these will be small. So the mathematics would be in the integral form, the mathematics is going to be the same as the one which we used for signal separation problems, as long as the mu k's are supported on disjoint arcs. Of course, we don't have Fourier moments, and so we have to estimate this integral using samples, but that can be handled using concentration inequalities in a clever way. So here is a reality check. We have 3 point measures with a very small probability of happening, and then there are 2 sums of uniform distributions happening with high probability. And we are looking at a sample size of about 12,000. So here is how the original measures look like, and here is our approximation. And you can see that it is estimating the support quite accurately. In fact, it's actually approximating the distributions also fairly accurately. But this time our interest is not in approximating the distributions. Our interest is in more in approximating the supports. So then the new insight which I developed together with Ryan is that our techniques can actually work with an arbitrary compact metric space. We don't even have to restrict ourselves to the Euclidean space as I had done with Alex Cloninger. So even if we have a compact metric space, we can always rescale it so that the diameter is less than pi. And then we can just use the trigonometric polynomials again. So this is how I would denote the ball. And again, this is the reconstruction kernel which I had described before. But this time I'm going to apply it to the distance between x and y instead of x minus y as before. And because I'm interested in estimating the supports and not the measures themselves, then it is convenient to look at the square of this kernel. If you are interested in approximating the measure itself, then there is a very old result in approximation theory which tells you that positive operators are not good. They will achieve a saturation. But we are not interested in, so if you are interested in approximating the measure, then you should be using this kernel. But we are not, we are only interested in approximating the support. So we use the square, but nevertheless the, oh, how is it? Nevertheless, the same localization estimate will hold. I think I should have written a 0 here. Not, I think it should be a 0, not a 1. Okay, so now we have a unknown measure out of which my data is coming. I'm just assuming that this unknown measure is supported on some known metric space M. And following my paper with Alex, we will call this measure detectable if there are these 2 conditions are satisfied. So the measures of the balls should not grow too rapidly. And if we are in the support, then they should not be too small either. So one example which is motivating is that our metric space is the whole Euclidean space. Oh, well, this is not compact. we have to project it down to the sphere to make it compact. And then X is the compact manifold of dimension alpha, and mu star is the Riemannian volume measure of X. We don't know where this manifold is. That's the important thing. But if we have such a manifold as our set of labels, then it will satisfy both of these conditions. And the mu sub k will be the probability of the class K. I don't want to assume that the classes are disjoint. So we make such a more elaborate definition. We will say that this data measure has a finite structure. First of all, it should be detectable. And then for every level of minimal separation, we should have a partition like this where the sets of the partition are separated by 2 times eta and the remainder is tending to 0. There was a lecture by Das Gupta where he claimed that all kinds of classification problems are really properly hierarchical classifications. So at one level, we are all people, which can be distinguished from inanimate objects. At another level, I am me and Emily is Emily and Michael is Michael and so on. And then at the next level of classification, this is my nose and these are my eyes and such. So this classification is necessarily hierarchical. And that's the idea here. At a coarse level, we have certain classes which are well separated. When we go, we could make this minimal separation smaller and smaller. And then we will capture more and more fine features of the classes. But okay, in the paper we have described exactly what this should mean, but in the illustration I will assume that my classes are already separated. Okay, so here is the analog of the point source signal separation theorem. Once more, I consider a thresholded set here. But remember, I don't have Fourier coefficients anymore. All I have is the samples xj, So all I can do is to construct this set. We can prove using the same ideas as in the point source signal separation together with some discretization methods from probability theory that there is such a R depending upon the threshold, so that with high probability this thresholded set is already approximating the actual support of the data measure. The actual support will be contained in this, and this is contained in a 1 over n neighborhood of this actual support. I'm still wondering whether such a theorem can be used in practice to determine what this support set is. But okay. So then once more, analogous to the signal separation theorem which I showed you, if this has a finite structure so that there is a minimal separation, then and you choose n to be greater than reciprocal of the minimal separation like this, then there is with high probability the partition containing exactly as many subsets as there are classes at this level of minimal separation, separated by the minimal separation condition and which approximates each of the supports of the class K. So the support of the class K at the level eta will be contained in this partition set, and this partition set will approximate that support. The interesting thing is in theory, we don't have to know how many classes are there. In fact, for different levels of minimal separation, there will be different number of classes. But this, whatever that number is, this is the output of our theorem. And again, I want to emphasize that this is very much analogous to the point source signal separation theorem. In fact, we can think of it as a generalization of that theorem. Okay, so here is how Ryan converted it into an algorithm. It was again based by an algorithm in my paper with Alex, but modification, because now we are not on the Euclidean space, we are on an arbitrary metric space. And so there is no Hermite polynomial or anything like that. But nevertheless, the idea is like this. We will create a set of confident points by looking at our data set and this thresholded set. Then we will choose the right points X in each of these clusters and extend the label for each of these clusters. And then we will extend the class labels to the remaining point by just a function approximation. But here we don't have classical function approximation algorithms. We are only in a metric space. So we can just we have to use just a nearest neighbor algorithm. And because we use K to denote the class label, we use the number of nearest neighbors by K bar. Okay. So then here is the algorithm. We treat this n and theta, and there is a p, which is the size of the cluster. Then we are going to construct a graph from our data set intersected with this thresholded set. There is an edge between these two if the distance is less than eta. And then we take connected components of this graph. Then we treat them as the cluster and choose the query by looking at that point at which our estimator, the sum of phi and square, is a maximum within that cluster. And then we extend the label to every other point in the cluster. This is not exactly consistent with the theorem, but it seems to work in some applications. Okay, after this procedure is finished, then there will be still some points which are left over. They are not part of any cluster of sufficiently large size, and so we have not classified them yet. Or otherwise it can happen that when we reduce this minimal separation, then some clusters will split, or they might have different labels within the same cluster, in which case we have to discard it. So that will leave certain points which are not certain. So when I was writing my paper with Alex, then instead of calling confident points, we called them certain points, and the others were uncertain, which means that certain points were certain and certain points were uncertain. So then we called the certain points to be confident points. And now, as I said, we are going to classify them just by nearest neighbor. So we are looking at a nearest neighbor approximation. Okay. So then here is some reality test. We looked at 3 data sets. One is the document set with 10 categories with 100 documents per category. And then here is the graph of true labels versus the number of queries. So with about 51 queries, we are able to attain about 95%, 97% accuracy already. And here is the visualization of the actual labels and the predicted labels. In our paper, we have a more thorough discussion with a confusion matrix and other parameters. Then here is another data set from my paper with Alex. So we are looking at the Salinas hyperspectral data set, which is a 204-dimensional data set having 220,000 data vectors. And we picked 10 classes. I don't know why and how. But okay, that was, but I think that these numbers were, this was just suggested by Alex that we should do it like this. Then we applied two other algorithms. One is the land algorithm from Mauro and Murphy, I think. And the lend algorithm developed recently by James Murphy and his student Kabir. And this is the graph of the number of queries versus the accuracy. So then you see that the mask algorithm is not beating the lend algorithm, but it is much faster. It does beat the land algorithm when the number of queries increases. So with about 1.3% data set, we are getting quite high accuracy, I think 87.5% or something. Here is the Indian Pines data set, which Alex said is harder. This is a 200-dimensional data set with 5 classes, and it looks like this. Here is the accuracy by the number of queries with respect to the land algorithm of Mauro and the land algorithm of Murphy and Kabir. This should have been masked. I think I probably copied it from an older version of our paper. When I submit to you the slides, then I will modify this. But anyway, this is a numerical result. So for 211 queries, our algorithm outperforms both land and length in terms of accuracy as well as insubstantial in terms of the number, in terms of the runtime. Okay. So thank you very much. Yeah.
All right, let's smash that reaction button.
Oh, thank you. And I guess now we will start.